Hello engineers, welcome to Mechanical Training World channel. Today we will discuss about wind load calculations as per ASCE 716. So this is the part 2 video guys. In first part we have discussed about wind speed, how to calculate wind force and how to calculate wind pressure and how to calculate moments and stresses caused by the wind in a engineering point of view. So today we will discuss all the points related to ASCE 716 code guys. Before going to start this session, I request you to please subscribe and click on the bell icon. You will get notified if I upload any new videos, guys. So let's start this session. So in last lecture, we have seen how this formula came. That is Qz is equal to 0.613 V square. If you compare this formula with the ASCE 716 formula, so the code given some factors. So today we will discuss about these factors, guys. How these factors affect our wind pressure. So this Qz is nothing but wind pressure. So let's see. So if you open ASCE 716 26th chapter and clause 26.10.2, you will find this wind pressure formula, that is 0.613 kz kzt kd ke into v square. So here kd is the wind directionality factor and ke is the ground elevation factor and kzt is the topographical factor and v is nothing but basic wind speed. In first part I have explained how to take this basic wind speed. So it is based upon the site location, guys. So client need to give this wind speed based upon the previous data, like 10 years, 15 years data. And next one is KZ. This is velocity pressure exposure coefficient. So we need to discuss all these factors one by one, guys, in a detailed way. So you will understand how these factors affect our wind pressure. So before going to that, I need to confirm you one more point. That is, if you open the code book ASCE 716 29th chapter and the clause 29.7, so this clause sets a minimum threshold for wind loading to ensure safety, especially when calculated wind pressure is very low. So if your calculated wind pressure as per this formula is less than this 16 lb by feet square, then you need to consider wind pressure as 16, guys. So you need to consider 16 lb by feet square if your wind pressure is less than this value. So anyway, if your calculated wind pressure value is above this value, you need to consider that value. So this is the important point as per ASCE 716 29.7, guys. So your minimum wind pressure should be 16. So keep that in mind. So next one we will discuss about wind directionality factor. Wind directionality factor is indicated by KD, guys. You can take this KD factor from table 26.6.1 from ASCE 716. So this KD varies based upon shape of your structure, guys. So this KD mainly depends upon your shape of your structure. If you are designing for buildings, your KD value is 0.85. If you are designing for arched roofs, your KD is for 0.85. So anyway, we are designing for tanks, right? That too for round shape. So for round shaped tanks, our KD value is 1. For hexagonal or square shaped tanks, our KD value is 0.9 and 0.95. This is how you need to take KD value from this table, guys. And next one is velocity pressure exposure coefficient. This pressure exposure coefficient depends upon exposure category, that is B, C, D, guys, and the height of the tank. So this KZ value depends upon mainly two things. One is height and one another one is exposure category. So let's see what is exposure category. So this exposure category deals with your location. So anyway, the exposure category A is absolute from ASCE 716, guys. So now we have BCD. So if your tank is located near city centers or residential zones, that is in urban cities or trees areas or where obstruction is there, then you need to consider your exposure category as B. So here wind speed is very low, guys, because all our obstructions are there. I already told you, if obstructions are there, your wind speed reduces. If there is no obstruction, your wind speed increases. So keep that in mind. Here you will feel lower wind speed. If you see in this table, the KZ values are very low compared to C and D. And if your tank is located at open fields like airports, coastal areas, that is low obstacle areas. So here wind is less obstructed. That means higher wind pressure you can observe in this location. So then you need to take exposure category as C. So here you can see your exposure values, KZ values as somewhat high compared to B, guys, because in urban areas you will have full of obstructions like buildings, trees. In exposure C, you have little bit obstructions only. So that's why your values is higher. If your tank is near to the sea or deserts or lakes where there is no obstruction, there is compared to B and C, there is less obstruction in exposure D. So you need to consider this exposure category as D in that point of view. So if you see here, your kz value is higher. So the factor is increasing because your wind speed is higher at these locations. So this is what exposure category says, guys. So your kz value depends upon height of your tank and these exposure categories. If your, for example, if your tank height is 300 feet and your exposure category is D, you need to take 1.73 as your kz value in pressure equation. So this table you can find in 26.7.3 from ASCE 716, guys. So the velocity pressure coefficient kz is higher for more open terrain areas. So that means exposure D. So this is all about velocity pressure exposure coefficient. And the next one is topographical factor. So before that, I need to ask you one question. That is, what is topography? So topography means that physical features of your land surface, whether your tank is located at hill region or riverside regions or lakes regions or mountain regions. So topographic depends upon land surface, guys. So because if you are mounting your tank at mountains region, so at that wind pressure is high, right? Or hills region, your wind speed is high. So if you are increase the height, the wind speed is high. So this is what your topography says. So the topographic factor KZT, the topographic factor KZT account for wind speed up effects caused by your terrain features like hills, ridges, escarpments. So this feature can accelerate your wind, guys, as it flows over them and increases wind pressure on the structure located nearby or on top. So let us see topographical factor KZT equation, guys. So your KZT equation is equal to 1 plus K1 K2 K3 whole power 2. This is mentioned in 26.81. So here K1 depends upon the height of the hill or escarpment and K2 depends upon the shape and location of the structure related to the terrain feature, and K3 depends upon the distance from the crest of the hill or ridge, guys. So you must use these factors, these three factors. So the site is on or near to hill, ridge or escarpment, and your terrain meets the conditions as mentioned in the 26.8.1, guys. So this is the table which gives you K1 and K2 values. There is one more table also there. There you can find K3 value, guys. So this K1, K2 and K3 values depends upon the escarpment, ridges and 26.8.1 conditions, guys. So if you satisfy the conditions, you can use this K1 and K2, K3 values. Otherwise, your KZT value is 1. If the site does not meet the conditions which is mentioned in 26.8.1, your KZT value is 1. That means no wind speed of effect is considered. This is all about topographic factor, guys. And next we can see ground elevation factor. You can find ground elevation factor from table 26.9.1. So this ground elevation factor KE adjusts wind pressure calculations to account for changes in air density at different elevations above sea level, guys. So this ground elevation factor depends upon one thing, that is ground elevation above sea level. For example, this is your sea, this is your ground, and this is your tank. If the ground elevation of your tank matches the sea level, that means 0. So then your KE factor is 1. That means ground elevation factor is 1. Or if your ground elevation is above the sea level, that means your sea level is 0. This is 0, guys. If it is somewhat high than this sea level, for example 2000 feet, then your kz value is 0.93. So this ground elevation factor completely depends upon your ground. That means above sea level, not on height of tank, guys. This is not height of tank. This is your ground elevation from the sea level. So at a higher elevations, air is less dense, which means wind exerts less pressure. I already told you in part 1 video. So at lower elevations, air is denser, so wind pressure is higher. It is permitted to take KU value as 1 for all elevations. This means for most practical designs, especially at low elevations, you can ignore the elevation factor, guys. You can ignore this elevation factor for particularly at lower elevations. So you can take KU value as 1. So this simply says that calculation significantly affecting the safety. So we are taking this as worst condition, because if you see in this table, so your kg value is less. So if you are taking 1 means we are thinking about worst condition, guys. So this is all about ground elevation factor, and I hope I completed all the factors, that is kz, kzt, kd and ke, which is given in 26.10.2. So so once you find the wind pressure, next we need to calculate wind force. So from theory, we calculated wind force as F is equal to Qz in D into H. So this formula I already explained in previous lecture, that is in part 1. So if you compare this with the code, that is ASCE 716, the code given formula is Qz into G into Cf into AF. This is something, this AF is nothing but D into H, guys. But you can see here there are two new factors came into picture, that is G and Cf. We will discuss these factors in detail in next lecture, guys. Thank you, guys.